Okay. Hello everyone and welcome to this lecture about 5G and IoT. And today I will also give a sneak peek into 6G. Maybe you have heard about it already during the course this year, but you will hear about it today. So my name is Anna Larmo and I work at Ericsson. I used to be in research until end of April, and now I have started as a strategic product manager for Ericsson dedicated networks. So that's more on the product side, so it's a new field for me. But today we will still talk about more research topics, 5G, IoT and 6G. So let's get to the agenda then. So first of all, I just want to give a very brief intro to Ericsson. And then we're going to go into the 5G and the status of 5G in the world. And then we're going to go to talk a little bit about IoT and going beyond simple IoT use cases and then merging the two topics, 5G and IoT, as was the topic of the lecture. We're going to look a little bit into the different 5G variants that are designed for IoT purposes and their technical properties. And then I have a few example use cases for smart manufacturing. And finally, we're going to have that sneak peek towards 6G and then summing up. All right, Ericsson, if you don't know our company, it's an old company, more than 140 years. And here we have a nice set of pictures showing the history and the development of communication technologies that Ericsson has provided. It's a great company to work for, that's my experience. Okay, let's go on to the 5G topics then. So this course, you've already learned about 5G. Just to recap, 5G basics. So it's a communication system comprising of several parts, such as the radio access network, the core network, and terminals. And then there are, of course, system aspects that are being standardized. And all of this is being defined and standardized in the 3GPP by hundreds of delegates from a large number of companies. And there's a picture of the spec. That's how they look like. You can find them online. Looking a little bit recap into the wireless access evolution, and the timeline of 5G. So 5G starts with the specification called Release 15 in 3GPP. That's the initial 5G spec. It was done around 2017, 2019. It was completed in 2018, actually the formal freeze. And the second release was completed last year, release 16. And now the standards folks are working on release 17. That should be ready end of this year, roughly. And then the evolution continues to release 18. 3GPP is gearing up for that at the moment to start the work then after release 17. Ericsson Mobility Report is something that we at Ericsson come out with regularly, and the latest report then has some data on 5G uptake. That has been faster than expected. So we have the prediction for 2026 shown on this slide, and it shows that 54% of the mobile data traffic should go over 5G in just a few years' time. And we should be at 3.5 billion subscriptions. And 40% of the subscriptions as a whole, we are predicting will be over 5G then. Covering 60% of world's population, this is quite significant. So 5G is gaining ground. On the left-hand side, you also have the green box showing the split between IoT and mobile subscription. And here we can see that 5.9 billion would be cellular IoT connections. So this is a big amount of IoT. Okay, that was a short recap in the 5G basics. Let's go to IoT basics then, next. So just some buzzwords that are related to IoT typically. We have sensing and actuating. This is the very basics of IoT. So we want to sense something, we want to actuate something. Then we want to communicate to that sensor and we want to control it, and this is the actuating part. And then when we are communicating, we're usually collecting data, and then we need to store that data somewhere and analyze it. And then we do computation on the data and we can do prediction. And that's how we are getting a little bit what I would call more beyond IoT. So I think the right-hand side of this slide is showing basically or is it left here, the basic IoT, and then when we go into applying machine learning, applying artificial intelligence, working on the full stack, then we're more going a little bit beyond the basics already. And that's how I think we should see IoT today. So IoT has been around for a long time. Even in cellular systems, we started with IoT more than 10 years ago. And first it was really about just connecting these sensors and being able to change the properties of the sensing mechanisms. But when we are moving now to today, we see more and more real-time sensing, automated sensing, automated actions and learning on the data. And this is something that's well beyond what we originally were talking about. So that's the state of IoT today. And that takes me to the next slide, actually. So I think we should see IoT moving more into a control system. And really, it's about controlling. We want to control things, anything that moves or changes in time, that has dynamics. And the control ensures then that these dynamics are functioning properly. And then we also want to manage, command, and direct other systems based on the information from one system. We can have open and closed loop control systems and feedback. The picture is showing a typical control loop. So we have input parameters, and then we have the output and feedback, and this is how we are basically controlling different things. And then how IoT relates to this is that we are actually implementing this very simple control loop, but over the internet now and on all these devices that we want to control. Okay, and then there are of course different constraints and requirements, and this is very important. Because then it's a question about how fast do we want this control loop to work. And typically, the more real-time control we want to have, the more stringent those requirements on the control loop are. And here we're talking especially about delays. So we want it to be as fast as possible to reach a real-time control. And then we also want to reach reliability, a high reliability. So we don't want those control messages to be lost. Those are two key properties. Yeah, so then putting that into the IoT context, anything that benefits from a connection will be connected, and then when we have a connection, what benefits from that? So it's basically any item that we want to get information from that provides input to these decisions through measurements or sensory data. And then any system that should get that input, and then any system where we want to put that input into action. So IoT is in essence a control system. Okay, we have some key technology choices then. So and that's a little bit summarizing what we already discussed. So why are we connecting things? We want to get the insights into the data, and then we want to store it somewhere. And use it somewhere else. And then there are these different devices we're connecting. And then the big question is, how should we connect? And of course, then we have the different choices on communication technologies and protocols and so on. So let's look at a few examples of what are we connecting over the cellular network, for example. So here we have some use cases for something we call in the 3GPP world the massive IoT. So there are smart home use cases, smart buildings, connected industries, agriculture, connected health, and so on. So these are a lot of use cases where we have a need to measure and collect a lot of information. It's maybe not so time critical, but it's very much about getting a massive number of sensors out there and being able to get a picture of what is the status of all these different systems and devices. And one requirement that comes with the massive IoT is for example, the coverage. And here I have an example then about how a coverage requirement may vary between different use cases. So we have the coverage here on the x-axis with the increasing coverage on the left and smaller coverage on the right. So coverage is like the range. How far do we want to communicate? And then there are some use cases here. So if we're talking about use cases such as agriculture, forestry, environmental monitoring, maritime, then we're talking typically about rural areas. We are somewhere out there in the woods or in the sea or in the fields, and distances are long, right? So this is where we have something one could call even extreme coverage. So we want to communicate from very far away. And then we can move to the other extreme, which is these very tiny devices where we could have something like diagnostics, treatments or health monitoring, access control, authentication. There we're talking about something where we need to be very close. So we need to be just a few centimeters away or maybe a couple of meters maximum. So you can see this coverage requirement alone can vary a lot between the IoT use cases, depending how far do we want to communicate? What is the actual use case? So when we design a technology, then we need to meet the whole range, right? But this is just one requirement, of course. So then we have many other requirements as well. And here, this slide is listing some other requirements that industrial IoT use cases, for example, might have. So they might require a certain coverage, first of all, but then there are other requirements that the technology needs to fulfill. It might need to be integrated into the brownfield solutions that are already there. We might want to know exactly where the device is, so we would like to have precise positioning. We want to maybe use Ethernet and time-sensitive communication over the link. We might want to have a specific industrial chipset required that is certified in a way. One very important requirement is also the guaranteed upper bound latency with limited jitter. And sometimes industries also want their data to stay on-prem, so this puts requirements on where we can deploy the network nodes that are actually storing and handling that data. So this is just a more comprehensive picture of all kinds of different requirements that come with the different IoT use cases, and much beyond the coverage as such. And just to show an example, then we have some use cases here that we are addressing with the Ericsson private 5G in the industrial space. that have more advanced requirements. So we're talking about manufacturing use cases, mining, ports, oil and gas, energy plants, and airports. So IoT is really expanding now, much beyond the simple sensing and simple sensors and actuators, to more industrial control. And the 5G network is then also developing into more like a network that can serve different kinds of use cases. And then we have done this kind of segmentation at Ericsson then for the IoT space. So we have segmented into 4 multi-purpose IoT segments. And you can see the massive IoT there in the blue square, and that's really where it all started. The low-cost devices, small data volumes, extreme coverage. But now we are then moving across the different colors towards the industrial automation. So broadband IoT is the next step. That's kind of reusing many of the properties of the mobile broadband that is used by your mobile phones today, enabling video surveillance and large data volumes, larger data rates, so going a little bit away from those properties that the massive IoT was optimized for. But then we also see that we need to move to serve those industries that I just showed in the previous slide. We need to move towards something we call critical IoT, which is then enabling this bounded low latency with ultra high reliability and enabling then the industrial use cases through that. And even beyond that, we have already standardized in 3GPP some aspects of the industrial automation IoT. So this is really taking even a step further and integrating to the Ethernet protocols, enabling time-sensitive communication, providing sync, accurate sync. So these are some things that are being worked on and will be enabled in 5G in the next years. And in the slide then we are listing some different industries there and which of these 4 segments is applicable to which use cases, and really showing that with 4G we could already reach the blue and the green boxes, but really you need to go to 5G to reach the orange and the purple. Okay, then let's have a look at the mobility report again, and in the report we also have this cellular IoT connectivity growth forecast. And I think this is quite interesting. It's now a very small font, sorry about that, but it's basically showing how the 5G adoption is already taking off in the IoT space. So if you look at this is from end of last year, but if you look at the 2020 numbers and the 2021 bars there, we are already reaching as many 4G, 5G broadband and critical IoT connections as we have for the legacy 2G, 3G. So that really shows, I think, that 2G and 3G were not designed for IoT, and they have been used for it anyway because there was nothing else available. But 4G, 5G, now that they are taking off, they are very quickly overtaking the legacy systems there for these more demanding use cases. Then we also have some predictions on the numbers of devices. And there we can see that the wide area IoT is kind of growing rather quickly, and the short range IoT is also growing, but not as quickly. But in total, basically, the IoT technologies are really one of the important parts of 5G. And really, I think this shows that 5G design has succeeded in addressing the market for IoT. Now going back to those 4 segments, I have an example here still on how you can even see then these different use cases in one vertical. So it doesn't mean, if you have a smart factory, it doesn't mean that all of your communication would be, for example, critical IoT based. But as we can see in this picture then, you have a large number of devices that we can sufficiently serve with the blue, with the massive IoT segment. And then we have a number of use cases where we're going to need the broadband IoT, the green one. And then we also have devices where we need the critical IoT, and those are, for example, the automated guided vehicles or automated autonomous mobile robots, AMR. And then we also have use cases that even require this most advanced mode of industrial automation IoT. And that would be then the collaborative robotics. And if we want to make those wireless, we would need to have all of those capabilities in the network. Okay, next I will go through the 4 different segments with a little bit more technology focus. We will keep it quite short, so there's a lot of detail on the slides, but we will not go through all of the details. But so that you get the idea, I will flash through these. So first of all, we have the massive IoT, and there we are typically talking about Cat-M and narrowband IoT modes. Those have been around already in 4G, and they are of course part of 5G as well. And there we were talking exactly about this. These technologies continue to evolve then to get even better coverage, even lower battery life, lower complexity devices, flexible deployment. And the focus is on wide area for these technologies, and they are usable for all industries. This slide is from last year. I haven't updated the numbers, but basically there are a lot of more than 100 networks already, more than 120 in 40 markets, and the technologies are well adopted in different industries already. Here's a bit more detailed comparison. I mean, this is a question that often comes up, that what's the difference between narrowband IoT and Cat-M1? So both are addressing similar types of use cases, but the narrowband IoT is the more optimized for longer coverage and lower power consumption. And it doesn't support, for example, voice services. In the 5G era, it's possible to have these technologies as part of the 5G deployment. It will just require that you have the 5G EPC. And we have some links there to the technical references where you can find more information. Then going on to the broadband IoT, this is the segment where we want to reuse a lot of the functionality that we have in the mobile broadband system already, and that is serving the mobile phones and the laptops and the like. So here we talk about LTE and NR technologies, and we talk about multi-gigabit transmissions, so high bit rates, low latency, lower than for the massive IoT, high uplink capacity, also coverage extension. This is also interesting for wide area, and extended battery life. And these are some of the focuses for this segment. And some use cases for IoT, we can mention cooperative intelligent transport systems, utilities, smart grids, trains, public safety, drones, advanced wearables, all these kind of use cases. Then moving on to the critical IoT for time critical communications. So this is now the more advanced mode that comes with 5G only. And here we're talking about adhering to a latency bound. So the figure here on the top shows that that for mobile broadband traffic we usually have a long tail of longer latency basically. And this comes from different protocol levels of retransmissions, different interruption sources that cause those, and so on. And now we want to squeeze that, we want to cut that tail basically. We want to have a bounded latency where we put a limit. In the figure we're showing 30 milliseconds. And we want to be able to deliver most of the packages within that bound. And then we can set different numbers. In the picture we're showing an example of 3 nines, so 99.9% of the packets should be guaranteed to be delivered within 30 seconds. Okay, 3GPP has worked hard on this for 5G, and we can see here the evaluation results on the lower part of the figure. The purple dot where we have 5 nines and 1 millisecond one-way latency, we can show that we can reach with release 15. And then release 16 evaluations show even more than more capabilities. And I'm not sure what is on the x-axis actually. Is it milliseconds or slots? But yeah. But anyway, so you can see that release 16 really expands the toolbox and gives us much more options. It gives a higher reliability, and it also allows setting the bound into different places. So that gives a nice toolbox for serving this kind of time-critical communication. How is this done actually then? So then we come to these low latency features in 5G. So just recapping quickly through this, we have the numerology of NR, the new radio. We have the short transmissions. We have the grant-free transmissions. And then we have something called preemption, where we can cut an ongoing lower priority transmission in favor of the high priority transmission where we want to keep the latency bound. We also have high reliability features. There we have PDCP duplication, different antenna techniques, automatic repetitions of the transmission without waiting for an acknowledgement. And then we're also building a big toolbox for time-sensitive communication. And there we will have reliable deterministic flows with accurate time delivery for synchronization. And this is also giving some of the building blocks for Ethernet integration. Okay, and we also have a toolbox for deterministic scheduling, and this is very important because the scheduler is the heart of the radio system. So in the uplink, the deterministic scheduling works on something called configured grant. This is utilizing the grant-free transmission, and we are basically giving the UE a possibility to transmit at these configured slots, and it doesn't need to request for the access separately. So this is in essence giving a 0 millisecond delay in the queuing if we are very lucky with the timing of the packet arrival. In the downlink we have something similar, but it's called short downlink semi-persistent scheduling periods, and they go down to 2 symbols. And multiple downlink semi-persistent scheduling configurations can be applied per bandwidth part. And in the upper picture we're showing that you can have also multiple configured grants for the uplink for the same UE. All right, moving on then to the industrial automation IoT next, and this was the most advanced feature set that we have so far in 5G for IoT. And this is really about integrating 5G with advanced industrial automation networks. And here we're talking about, so the work has started in release 16, so the first parts are already standardized, and now it's continuing in release 17. And here we're talking about real-time Ethernet integration, time-sensitive communication or TSN, and clock sync as a service. And here we want to address really the most advanced use cases for IoT, for the industrial IoT. So we are talking about use cases like the most advanced cases in manufacturing, like I showed before, the collaborative robotics, for example, and controlling robots over the cloud. We talk about remote control in mines, automating utilities, maybe in the distribution automation systems. We talk about offshore and ports, and there is even a industry fora that's called 5G ASEA, 5G enabled connected industries, that is really focusing on this and bringing together the companies that are working in these industries and that are working in ICT, and jointly discovering the solutions that we need to really make this wireless. Okay, I will show some more details on the 5G and how would you realize a network for some of these use cases. So then next we have the core deployments for critical IoT, and here we are showing what kind of impact the placement of the core network has on the latency. So on the bottom part there you have the latency, and then you have the different deployments, and on the left hand side the deployment examples tell you where does this apply. And then the different colored boxes show what function is placed where, and we have many different options, right? So the typical public network deployment would be the top one, the number one, wide area. And there we are having a national data center where we have the core control plane, the network exposure functions, and the subscription data management. And then we could have a regional data center in larger countries where the user plane node, the green box, would reside. And the cloud application server can be outside of the network, and then you can have an application server also co-located in the regional data center. And then you can see here that the more local we become, the shorter the round-trip time comes. So for the national data center case, where we have the core network furthest away from the actual device, we are showing here, for example, that the round-trip time could be around 10 to 40 milliseconds. And when we bring all the possible functions down to the premise, the number 4 case, we can really reduce that round-trip time from those hops that happen in the core network side then. And we can basically eliminate that delay from the round-trip time. So this is something to keep in mind. It's not only the air interface that has an impact on the latency, but it's the whole deployment and how you are, where you are placing your nodes. Okay, that was about core network, and then another important part for the whole deployment is the spectrum. And there we can talk about 5G NR a little bit and how 5G NR really enables critical IoT then in all its frequency bands. So for LTE we have the green boxes here, and you can see that they are only available, LTE is only available in the low bands. For the mid band and the high band we will need the NR, so the 5G standard, and there we have spectrum available, and we have much more spectrum in the mid band and the high band than we typically have in the low bands. So this is really an important aspect as well. That what kind of spectrum do you have available in your local area to realize this deployment on? And that may also impact the choice of technology. Okay, that was the technological part for the 5G. Now we looked into the different features and aspects. And finally, I want to show here, we have some recent demos from Ericsson that we have worked on with some of our partners for smart manufacturing. And there's links to the videos on the slides. Now, I don't think we can show them now. I forgot to prepare this. But you can check the links offline, and we have shown these 3 demos, I believe, in the Hannover Messe this year. So the first one is a 5G-based industrial robotics testbed together with ABB. And there we're showing how we're controlling the robot over the 5G interface network. And then we have also a testbed in the Bosch semiconductor factory. And there we're showing the autonomous mobile robotics. And we have a testbed in the 5G Industry Campus Europe in Germany. And there we are showing the milling process. And all of this work has been done in an EU project called 5G Smart, together with all these partners. And it's, of course, funded by the European Union. Important to mention. And these testbeds are also, by the way, approved as the 5G ACIA testbeds. But please check YouTube for these short videos. They are only a few minutes each of them. Okay, we're coming to the final part of the lecture. So we talked about 5G, we talked about IoT, we talked about putting those two together. Now, of course, we are going to 6G next. And this is really a big shift that will come then, and the research world in the wireless sector is already working on this new 6G definitions. And at Ericsson we are talking about the road to 6G, the journey, and we have identified some important aspects that we believe the 6G system will then have. And they are listed here in these gray boxes. I will show in the very end a few examples, but basically I will just list them now. So we are talking about the Internet of Senses, connected intelligent machines, digitalized and programmable physical world, sustainable world, limitless connectivity, trustworthy systems, cognitive network, and network compute fabric. And out of those, the journeys that I believe are most relevant for IoT are the number 2 and 3 in this list. So we have the connected intelligent machines and the digitalized and programmable physical world. So that's where we're really taking advantage of the IoT and enabling the future IoT. All right, now taking a small step back, let's try to connect the telecom and industry evolutions and how we are getting into this 6G, ever-present intelligent communication in 2030. So if you look at the top bubbles there, you can see the evolution of the telecom systems, the mobile network. And you can see we have a new generation roughly every 10 years. So 1980s, we started with 1G, 1990s, 2G, 2000, 3G, 2010, 4G, 2020, now we are at 5G, and now we're starting to work towards 6G, which will hopefully be then reality in 2030. If we now compare that to the industrial evolution timeline, then we can see that in the industrial evolution, the generations are much longer. So Industry 1.0, some people may call it like that, was the mechanization. And that happened in 1780, so that's quite a long time ago. Then 100 years later, we had the Industry 2.0, when electricity was invented and the electrification came to the industry. And another 100 years later, automation was taking off, and people call it the Industry 3.0. Today we are talking about Industry 4.0, and that's about digitalization. And that's where we are saying that 5G is becoming very relevant. But what about then the future? So how long will this cycle be? So you can see already now that from 3.0 to 4.0 we accelerated by 50%. So that took only 50 years. And now we believe the acceleration is increasing. So maybe the Industry 5.0 will come even faster. And 6G really should be designed to already meet the demands of this kind of very personalized production that we see in the Industry 5.0 timeframe. There has been some work done in Europe, European industry on the Industry 5.0. You have a link there on the slide. And of course, as I mentioned, 6G work is starting, and I have later in the presentation a link to our white paper on the topic. Now we have a couple of minutes left, so let's go very quickly through the rest of the slides. It's not too many, but just to mention, I mentioned the 5G ACIA as part of the Industrial Automation IoT and the most advanced track. So they have also started to look into 6G and think about what do industries need in the 6G time frame. And there is a position paper already available that you can check from the link in this slide. And it's talking about this, that how 6G should have a continued strong focus on vertical industry applications and requirements. We should strengthen the non-public networks, the private networks. We should be backwards compatible and so on. So I think these are very good points that are being lifted here from the industrial players, and really it's good to have them now when the 6G work is starting so that we can design a system that actually meets these demands that we are seeing in the field. Then jumping back to the Ericsson scenarios for 2030. So this is just a recap of those that were in the title slide already for 6G. We had these different use case scenarios that are enabled by this network platform. That was the Internet of Senses, connected intelligent machines, digitalized and programmable physical world, and connected sustainable world. And then on the bottom row we have the technology scenarios that are then evolving the network platform. And that's where we focus on technology development to reach limitless connectivity, trustworthy systems, cognitive network, and network compute fabric. And then I mentioned already earlier, from the top row, the two middle ones, the gray and the red box, they are the ones that are most relevant for IoT, I believe. So I have one slide on each. So first we have the connected intelligent machines. And here we're talking about the separate parts of the digital world that are merged through the physical networks. It's a lot about flexible manufacturing, interaction of robots that are autonomously moving in the world, and autonomous systems and AI in general. So this is the focus. So we're going even more towards autonomous control without the human in the loop anymore. And we can see these IoT systems then evolving on their own, basically based on AI and machine learning. In the digitalized and programmable physical world, there we see that we are syncing the physical and digital worlds with sensor and actuator data. A very common example is the digital twin that many people talk about today. And then we can enable new use cases like precision healthcare, interactive 4D maps, and sensor infrastructure web, where we have widely distributed sensors that can provide accurate real-time sensor data, which is as reliable as an onboard sensor data. So these are very exciting two fields that where we see IoT will further develop then in the 6G timeframe. Okay, wrapping up with the summary slide, what I would like you to take away from this lecture: 5G is a well-established IoT technology today already. And in the IoT space, we are moving beyond the simple cases with automation and advanced use cases. And 5G is already powering industries as well. But we have also started the journey towards 6G, which will enable even more advanced use cases and more autonomous systems. And our vision for the 2030 and 6G includes then this massive communication between intelligent machines and a truly digitalized, programmable and sustainable world. And this vision for 6G is well aligned with the vision of Industry 5.0. So that's the next generation in the industry space. And as a final note, I can just advertise the Ericsson 6G white paper that was released end of last year. And there you can find more details about our 6G vision. That's all for today. Thank you very much. And do we have questions, time for questions, guys, or how should we go?
At the moment there's no questions, but I think we can expect some to the Zoom chat, but I think let's wrap up the lecture from here and let's continue maybe looking at the Zoom chat later on.
Okay, then thanks a lot.
Hello everyone and welcome to this presentation. The title of my presentation is Cybersecurity and 5G. My name is Seppo Virtanen and I'm an Associate Professor of Cybersecurity Engineering at the University of Turku. The outline of my presentation is here, so I'm first starting with some definitions regarding cybersecurity and information security, then talk a little bit about intrusion and intrusion detection and prevention, then focus on smart environments and IoT and their cybersecurity, which is a very key application area in terms of 5G, and then conclude with some 5G specific considerations for cybersecurity. First of all, let's define the terms cybersecurity and information security. So we all know that these are often used as synonyms in the spoken language, but actually, if we really look at the details, so cybersecurity is a broader concept, and you could say that information security is one part of cybersecurity. So in cybersecurity, we are targeting a state where the operating environment that consists of one or more digital information systems can be trusted and its operation is secured. And the focus is then in considering network connections and network digital systems and the security and protection in these. And we are also talking even at the societal level of the security. So some factors in cybersecurity include information security, continuity management, for example, in businesses, if there is some disruption or an attack against some business. So continuity management aims to preserve the operations as well as possible in those crisis situations. Also, at the society level, we can have or should have preparedness for different kinds of crises in terms of cybersecurity. For example, if electronic voting would be used in governmental elections, so that would be something that requires this preparedness if there's going to be a cyber attack, for example, against that sort of system. Whereas then in information security, we go a bit more into the detail level so that we make the arrangements to ensure that the availability, integrity, and confidentiality of information can be ensured. And the focus is on information and protecting the information. Some ingredients of information security include the protection of digital and physical recordings, human knowledge, and protecting data both in storage and also during data transfer. Very traditionally, the security goals are identified as this so-called CIA triad. CIA comes from confidentiality, integrity, and availability. Confidentiality means that the contents of or the data, the information is revealed only to those parties who have the privileges to access that information. So for example, by using specific kinds of encryption, we can ensure that only some specific parties can access and decrypt the information. Integrity means that the data that we have has not been tampered with, it has not been altered, but it's in the original format and content that it was when it was created by that entity who created it. So it has not been changed, for example, during transportation or in storage without leaving a mark. Finally, availability means that even though we ensure confidentiality and integrity of the information, we still also need to make it available. So that means that those who have the right to access the information will be able to access it, and also from another point of view, you can consider that some information is made available and we try to keep it available even if there is some crisis or attack going on. So we want for example, some web servers to be available even in those situations. So we need robustness and protection for those situations to make sure that the information remains available. So then how do we achieve the goals of the CIA model? We need to take into account both the technological and the human elements of cyber security when we store the information, when we process it, and when we transfer the information. And some very almost obvious things that we need to take into account is regular backups to make sure that we are able then to recover, for example, from broken systems if some systems fail and hard drives break, so we are able to restore the information. We also need to recognize the value of information, so even some very seemingly not so valuable documents may be valuable in terms of how many hours have been spent for creating this information, and so that needs to be protected both from attacks and then these accidents or devices breaking up. Then when we are considering availability and confidentiality, we need to find the right balance for those, meaning that we can't make information so difficult to access that it no longer is feasibly available. So this appropriateness in the levels of protection needs to be considered. Regular updates are of course very important, as well as protection against malware and unauthorized users accessing the system. And then the human element from the point of view of training the users, increasing their cybersecurity awareness, that should be done on site to make sure that, for example, that employees understand the local cybersecurity policies and have up-to-date knowledge about how they should deal with certain kinds of information. Encryption is, of course, a very good way of assisting us in reaching the different goals of the CIA model, both for storage and transfer. So then let's consider intrusion and then intrusion detection in computing systems. In the 1980s, you could say that the goals that hackers and malware authors had, they were mostly for showcasing the skills they have, how talented they are in programming, or trying to gain access to systems, or even making pranks to some friends or other hackers or malware authors. But then in the mid 1990s, the general public found their way to the network when Windows 95 and Internet Explorer came out, and suddenly now there was this tilt towards a situation when we have a huge number of network users that have some information that is worth money, and that trend has of course been getting stronger throughout the years. So nowadays everybody in practice has some information that is worth money, for example, in the form of online banking credentials. From that time also we saw the rapid emergence of online shopping and spam email. So when so-called regular users, general public, started using the internet, so then this was a great opportunity for, on the other hand, starting this business of buying things online, and on the other hand trying to advertise things online with spam email. And the malicious actors then at this time started also on focusing on some sort of gain, not just showcasing their skills or making pranks, but to financial and political gain. So the goals for a modern day cyber attacker often are either financial, for example, trying to fish for credentials using emails or fake websites or even malware. Also trying to steal them, for example, by using keylogger malware on some system, trying to distribute that, and then the keylogger records all the keystrokes in the system. Health records could be stolen, and then some ransom could be demanded for those not to be released. Identity theft and extortion are also forms of or ways of trying to get financial gain when doing cyber attacks. Then there are also political or ideological goals. For example, for some rival government or organization, try to generate the distributed denial of service attack against their their systems so that their servers and networks will go down and nobody will be able to access those. Or espionage. Some kind of similar methods could be used as for financial gain, but now when we are talking about financial gain, this is very often targeted at the general public. But in terms of espionage, probably the target is more precise, so it may be a specific group of people, for example, who are the target of this sort of attack. And then there is hybrid warfare, for example, trying to cripple infrastructure or influence general opinion, for example, in social media. So there are two main ways of breaking into systems, and of course, then these can be combined to get maximum effectiveness. So the technical side is when you try to exploit some technical weaknesses and vulnerabilities that exist in the target systems. This, of course, then requires some technological expertise. So one needs to know what sort of vulnerabilities have existed or currently exist in some systems made by some specific manufacturers, and then how these can be taken advantage of, and what sort of results can be expected in that situation. So there is time and effort required, especially if the target is not known beforehand. So to first do the research and figure out what sort of equipment is being used. This is often this technical way of breaking into system is often such that it includes also attempts for either breaking passwords or phishing for them, or using malware to catch some information that or allow access to some system. But then the other way is to exploit the human element, so-called social engineering, where you try to persuade a legal user to hand out information like passwords. And this, of course, then speeds up the intrusion process because you can skip some of the difficult technical phases if somebody can be persuaded to give you detailed information about the target you are attacking. It's really a big issue, these vulnerabilities. So here is some statistics that I have gathered over the years from the same source. Number of annually reported newly discovered vulnerabilities. So as you can see, they are on the increase all the time. So when we get new software, new systems, they often have some flaws that cause these vulnerabilities, and that's why we need to keep systems up to date and install updates as soon as we are offered them. Very easily you can find out then, for example, from many websites, you can figure out the server software version from the HTTP response status lines and these header comments. For example, here the server announces its version number, and then you could look, for example, for those possible vulnerabilities that are known to exist in that system, and if it's not patched, so then it may be still vulnerable for those. Like I said, so the server weaknesses and vulnerabilities, they are the result of flawed software implementations, or also they could be errors in configuration. So ways of taking advantage of these could be, for example, cross-site scripting, SQL injections, and then denial of service attacks, and a very specific kind of systems also relevant in terms of 5G and IoT is the supervisory control and data acquisition, or SCADA systems that are found in industrial processes and manufacturing plants, for example, to control some processes, and these often are required to be using some specific version of an operating system, and it may be very difficult to apply patches for vulnerabilities, even though these are usually in a separate network. So still there may be a way for a hacker to find their way in one way or another to these SCADA systems, and maybe even cause physical damage, like, for example, with the Stuxnet malware that was used some time ago to disrupt industrial processes. So then, of course, we want to prevent the intrusions, and for that we can use, for example, firewalls, and then special systems called IDS and IPS systems, intrusion detection and intrusion prevention systems. And also an important thing, of course, to try to prevent intrusion is to have a good password policy, so that the users will have to select passwords that are not easily guessed by the intruder. So then if we are intruded, so we want to detect this intrusion, then we want to mitigate its effects, and then afterwards we want to consider the effects. There is a quotation from a well-known researcher in the field that inevitably the best intrusion prevention system will fail. And so when the prevention fails, then we need to still be able to detect the intruder and stop the attack, and then detect the illegal user from the systems and remove them so that they don't have access and can't return. But then there are also plans needed for the continuity, and also a process for countering the attack, so that if something like this happens, the organization must have some way of trying to deal with the issues. And then afterwards, an evaluation of the events and the adequacy of the organization's own processes is needed. And one thing to consider is also physical information and cyber security. So if the attacker gains physical access to the premises, the target site, and the devices, so then they don't need to break so many technical barriers to achieve their goal. They can install, for example, unnoticeable spying devices using some wireless communication technology that then transmits data to the attacker. They could install malware on site, steal equipment, or destroy equipment, or something like this. Next, I'm going to talk about cybersecurity in smart environments and IoT, and for that, I first define smart environments. So here's a picture of a possible smart city, all sorts of things happening there based on IoT systems and smart technology, and the goal there is that these smart devices and systems work all the time, and their goal is to make everyone's life easier and more comfortable, and in terms of when we talk about cities, so to also optimize the use of resources. A very key area in all smart environments is data acquisition and analysis, and this data acquisition is needed because we want to obtain information and automate systems based on that information, so that we are able to enable these smart environments. I like to always say that we should consider these smart environments at different abstraction levels. So we have the smart personal space, where we consider, for example, things like measuring our own health related and well-being related data using smart sensors. Then we have smart rooms, where the room is aware of the user, and we could have, for example, home automation as a part of this smart room level. Then we go to smart buildings, where we have building automation. We could have office hot desking, meaning that when you just arrive at the office, you choose any desk and it recognizes you and makes all the adjustments and places, for example, the correct applications on your workspace, so that they are where you left them in the previous desk you used. And also then in the buildings, if there are common areas or public areas, so the safety and comfortability of those areas. And then we come to smart city and society, and again another abstraction level, where we then consider things like smart traffic, or even automated public transportation, automatic law enforcement, optimizing city or society resources, and even enabling e-participation. This picture here displays now one possible scenario of this sort of smart environment that has to do with all of these different abstraction levels. So there is a patient in a room. The patient's medical data is being measured by sensors, and then in this room there is user awareness, and this data is refined before it's sent to building level storage, for example, for the local caregivers to monitor the data and make decisions based on it. And then it can also be made available at the larger, let's say the city or society level, even, so that some remote caregiver can access the data, and some expert can, for example, then be consulted easily in this sort of environment. So like I said, the smart personal space is often dealing with health and well-being for the individual. And here, for example, you are seeing a smartwatch that is measuring the heart rate and the activity of someone using it. And then we could have, for example, automated insulin pumps or heart pacemakers that can even give you the defibrillation shock if there is some sort of cardiac arrest detected. In smart buildings, then you have automation for function and control, like, for example, automation for lighting and power sockets and door locks. Also heating, ventilation, and general status monitoring can be included in the smart building level. IoT also here is a very key enabling concept. And this is scalable, so it goes from detached houses to apartments and office buildings. So you could say that there's private smartness in your own apartment, but then public smartness in the common spaces and building level safety and security. For example, in case of emergency, the building could know how many people are inside and in which areas. Then when we go to the smart city level and beyond, so we are talking about innovative development utilizing ICT technologies, sensors and devices that gather information that is then refined into knowledge that can be used when we run different systems efficiently and use resources efficiently and conveniently. But now we are gathering data from many different sources, so citizens, devices, and systems, and then this is processed, and this, of course, then already starts to raise a lot of security and privacy questions. A smart city can't function if its design hasn't given attention to all the levels of abstraction in the smart environment. Data transportation is very important in smart environments, and here is just some examples of so-called war driving in a southwestern Finnish city. You can see that there are quite a few Wi-Fi hotspots around the city, and some of them are secure and some are unprotected and some have obsolete protection. But so we have this abundance of data transportation networks everywhere, and this is kind of maybe also could be considered using this resource in addition to 5G, for example, as a backup in providing for smart city communication. When we then think about these smart environments, we need to consider cybersecurity very carefully. If we are not able to make the systems secure enough so that the users will trust them, nobody will want to use those technologies. And that's why it's very important that we don't overlook cybersecurity when doing designs for smart environments at any abstraction level, even though we might have a rush to deploy the new technology so that we could get revenues from for example, manufacturing some new sensors or IoT devices. So the cybersecurity and safety concerns need to be addressed already at the earliest phases of the specification and design. And also the technologies will be or need to be such that the user gets a benefit out of them without making them vulnerable to any security and safety and privacy risks. So security should not be considered as a feature, but rather an emotional response to the overall system, so that you have a feeling of freedom from risk, freedom from danger, doubt, and fear, so that instead of just having a security feature in the system, you are able to have this kind of feeling about the system. In the smart environments, there are lots of concerns then for cybersecurity and privacy. For example, when considering health data, so when we are gathering data from patients and using that for deciding on treatment, either automated or by a physician. So this is very private data and it requires strong protections. But on the other hand, then the sensors and implants that are used for gathering this information and transmitting it, they are very limited in processing power and power supply. So we need technologies that support low power and lightweight, but still a strong encryption, for example. So the traditional security technologies are not directly applicable in smart environments where we might use, for example, 5G for data transportation. In this example, keys for encrypting traffic from the patient's sensors are derived from the individual's heartbeat, so that they are always unique and secure keys, so they do not repeat from one patient to another, but always unique for that connection. And this is one way of achieving secure cryptographic keys without having to do very heavy mathematical computations like in some traditional approaches. But then about this data privacy also, so one consideration is given here that now this smartwatch here is saying that the person who has been using it didn't sleep too well. Nightly recharge is compromised. So now if you wanted to get the most out of this watch, you would create an account with the manufacturer's online service, and then also probably, for example, sync it with some other ecosystem, like for example Google's system if you are an Android user. And so now then all your data is in these systems, and also the watch is on your wrist, and then in the morning on your way to work you drive off the road and you wreck the car. But now if the insurance company would know that you didn't sleep too well, so would they refuse to pay? So these are concerns for the future, that this data must be protected so that only those who really need to be allowed access to it have the access, and nobody else. Also, from the medical devices, if somebody would be able to break into the pacemaker defibrillator and then modify its settings, so then they could give this defibrillation shock for someone who doesn't need it, and of course that is very dangerous. And someone could also break into an insulin pump that has wireless settings and modify the dosage so that it will not be the correct amount that is administered to the patient. Again, very dangerous. If we go to then smart rooms and buildings, so in an interactive smart building, the building knows a lot of things. So it has a knowledge of history, like for example, the materials, the building process, and the maintenance history of the building, and then the current and historical data, for example, air quality and moisture levels, water quality and energy consumption, and the user profiles, how and when the users interact with the building and how they live. Many smart operations like resource management, for example, or scheduled maintenance, fault detection, air quality detection, of course, rely on this kind of data, but then on the other hand, this is data that might be very valuable to somebody, some malicious actor. For example, here you can see this continuous measurement of electricity consumption in one location, and because this is monitored on a daily basis in real time, so then from this graph you could see that on the year in question, around July 7th, the person who lives in this apartment has probably been on vacation because the consumption of electricity has been much lower than during that month in the other times. So this sort of information could be perhaps misused. Somebody might figure out that somebody is not at home and might, for example, commit burglary at that site. When we go to then smart cities and beyond, so we consider things like smart vehicles and smart ships, autonomous cars, and so of course the big question is that if something happens in these systems, for example, a person is hit by an autonomous car or a smart ship is wrecked somewhere on the sea, so who is liable for that, and how do we deal with these sorts of things? So those are very big concerns. Also, electronic participation in the society is of course something that also is a concern. So at the very best, it's very nice and convenient to have this e-participation, but on the other hand, there are risks like, for example, manipulation of gathered data and interference with the processes, for example, by using denial of service attacks. And when these sorts of events might happen, so then this might lead to the loss of public trust, so that the users don't want to use these electronic systems anymore, and then they are useless, and this trust in the e-participation system will be lost. Then if we consider from the point of view of the participant, the person in the smart environment, so pretty much you could say that the biggest security and safety risks often arise from the ways of the users. So the user habits and sometimes the lack of skills may lead to some vulnerabilities for non-technical cyber attacks, like, for example, social engineering. So somebody might be giving out valuable information that should not be given out to some external actor. So what is needed is an increase in the user security awareness and also convincingly mitigating the user security and privacy concerns, so that then we can build trust, and this way we can build more secure and safe smart environments, and these issues also need to be taken into account in the planning and design phases already. Like I mentioned, so smart environments rely on the massive use of diverse data describing the behavior of these industrial and societal systems, and also the individuals. And that means that we need to have trust in the systems that gather, process, transmit, and store the data. And this data may be very personal and private, so it needs good protection. Also, the environment may make decisions based on the data that have an effect on the entire safety of some environment, for example, or an individual. So, for example, these personal medical implants, automated traffic and public transportation, and even water, heat, and electricity as parts of some cities' infrastructure could be affected. When we are using technical systems, so we can pretty much expect that some previously undiscovered vulnerabilities are probable. And so what we need to do is we need to look at these cybersecurity, safety, privacy, and trust issues from all the abstraction levels. So from the point of view of the individual, the society, the infrastructure. So then let's look at this cybersecurity in the 5G context. Basically, almost everything I have been saying so far applies directly also to 5G enabled environments and communication using 5G. So in terms of smart environments, it will be very vital technology, enabling technology, especially when we think about the building abstraction level onwards. So we have the massive IoT and mission critical IoT types of communication for 5G, where we want to have low power consumption and, on the other hand, robust and reliable connections. for communication. So basically, if we consider the smart environment context I was talking about previously, so all the identified risks and threats apply to this 5G implementations of smart environments. So these are not just 5G technology dependent, but the entire system that uses 5G needs to be considered from this point of view. Then from the broadband user side, so from mobile broadband, 5G is expected to provide us with previously unseen communication speeds in wireless cellular network technologies. So no technology before 5G has been able to achieve such high speeds, meaning that with the low latency and high speed, this will be the de facto easy choice for many consumers who are looking for fast internet connections for the daily needs. And again, we are facing the situation that like with any internet access method, so also the risks in terms of intrusion and stealing information and having the financial, political, ideological goals in terms of hacking. So these will also apply to systems that are using 5G as the communication method. So then what sort of drivers do we have for this 5G security era? We have new service models here. So we have the high speed, that's for the mobile broadband, but then we have for the IoT side, we have the low power requirements, and then we have this mission critical side, critical reliability needs to be addressed. So new models, and all of these have different kinds of requirements for security. So we need for some systems we don't have to consider the processing burden so much as for some other environments where we have low power and not very high speed processing power available. So we need to have these lightweight solutions. The amount of data to be transported, processed, and stored will become huge with now moving on to 5G, because it enables this machine-to-machine communication, and that means that our machines will start exchanging data, and that means that there will be all sorts of devices that are sending and receiving data, and then there are the data privacy concerns that need to be considered. Again, like for most other ways of communication also. So if there is some private information, the privacy needs to be preserved. Also, the number of new network devices will increase very greatly. So we will have countless new devices like IoT devices, sensors, smart environment enabling devices, and we are getting into this everything always connected. So this means that we will have a huge increase in vulnerable devices and also the threats faced by these devices. So even if there is adequate protection at some specific level in the protocol stack, so if the device is poorly protected, so this will still be potentially dangerous, vulnerable for the entire users network. So a huge increase in types of threats can be also expected. So then how do we go about securing 5G? Distributed denial of service attacks against, for example, a specific cell tower. So detecting these, that's more maybe 5G system level consideration, but if there would be this sort of attack against the radio side, so then this would require rerouting the traffic and trying to mitigate the effects of the attack. When we think about then the 5G enabled devices around the world, so these millions of IoT devices could be then with some malware, for example, or if those devices are otherwise poorly protected, so these could be turned or made a part of some bot network, and this way a completely new attack surface is created. So we have millions of devices that could be then launching a simultaneous attack through the mobile network. So radio network protection from misbehaving devices is also essential and needs detection, logic, and intelligence. Building trust between the systems and mutual authentication between the user and the network is required. So the network can authenticate the users reliably and make sure that they are allowed to use the network. And on the other hand, the user is able to authenticate the network reliably so that the user will know that it's a legal network that is that the connection is being made to, and not some rogue cell tower, for example. And we are no longer just connecting humans and human identities, but now we are starting to talk about this machine-to-machine communication. So we also need to have ways of evaluating the trustworthiness of IoT hardware, software, and the configurations so that we are able to consider this communicating party reliable. Then when we talk about these small devices, sensors, and IoT devices using 5G, so we need to consider security from the point of view of energy efficiency. So on the other hand, we must ensure secrecy and privacy for data that requires it, while we also preserve power. So that means that we need to have lightweight approaches for cryptographic implementations. Privacy protection, I already mentioned, but then also this compartmentalization is very important, and this is managed, for example, with slicing. And on the other hand, we can also use cryptography so that even if some area or reserved bandwidth has been compromised, so with compartmentalization and cryptographic protection, we can still maintain the other compartments so that their operation is preserved. As a reminder about the connectivity in the network, so now when we talk about networks like 5G, so we are talking about this last mile protection encryption device. So we have the home user, we have a computer or a mobile device, and then this network protection is only for the last mile, but then we need to consider also the end-to-end level protection. So then multiple layers of security are needed, and encryption, it's not enough to have it just in the last mile connection, but then we need to also make sure that the end-to-end connection is properly protected so that the data will not fall into the wrong hands during transportation. So I conclude my talk here today, and I thank you for your interest in this topic, and my email address is showing here, and so if you wish to have further discussion about this, so please drop me a message. Thank you for your interest in this presentation.